Welcome, my fellow Cyberzins, to another Mighty Mini Monday. Today's episode is about containers, but it's about one of the core technologies containers are built upon. So if you're wanting a high-level containers, how to use Docker, leave a comment below letting me know that that would be useful, and I'll cover those later. But this is more about how containers work, how they're different than VMs, and actually it contains so much more information than I originally had planned on, but all of it I thought was really good information. So please scratch out the mini part of this and take this as your Mighty Monday for this week. All right, let's jump into it.
3, 2, 1, 0.
The No Channel.
So, as many of you are aware, containers are at the heart of Kubernetes, a subject that we cover a lot here on this channel. Although, again, Kubernetes is a pod scheduler. Just in case anybody thinks that it schedules containers, those are happy accident. Anyways, the containers are a core technology of Kubernetes. And so that being said, me personally, I've been exploring and understanding containers and how they work. Everyone knows that they work by namespaces and C groups. What does that mean? How does the kernel handle that? And what does it mean a container is? So let's explore that. The very first thing I'd like to do, the very first thing would be to explain the key difference between a container and a VM. Now, I know that there's about a bajillion places that you can go and find this, but if you're watching this video, I think that it was very useful to know this. So skip ahead about a minute if you already know and don't want to hear my explanation. Go ahead, just skip ahead. It won't hurt my feelings much. But if you don't understand this, listen to this, and this will help you understand what containers, how they're different than virtual machines. So virtual machines are virtual machines. They contain everything from the bootloader up of your OS. So this means they have their own kernel, their own OS, with its own kernel version, and everything you want to package inside of it. It's an entire machine. A container is not. So let's draw this out really quickly. We have our base machine here running VMs. And this is going to be split up into the hardware, the firmware, the bootloader, whatever. And then on top of that, we have, and I'll just draw that layer here. We have the OS that sits here. So whatever it is, your Ubuntu, your whatever, your OS. And then on top of that, you have some sort of hypervisor. Now, you could say like the difference between the OS and the hypervisor, especially with technologies like KVM, are very merged. The lines are blurred here as well because KVM kind of runs on your OS. So, but it is still separate. It's something you install separate. But it is empowered by your OS, and a lot of the kernel features are there to empower KVM. So anyways, you have your hypervisor. So you could have KVM or any of the other hypervisors out there. And then you have your VMs. And your VMs have virtual hardware. They have then their virtual OS. And when I say OS here, this OS can be broken down. So let's into kernel. Let's break this down into two squares here. Your OS it has the kernel. And then your OS has some higher level things And we're going to call this a user space. But bear with me, it's not all necessarily user space, but you have the stuff that runs in your kernel. And then you have everything on top of that, where you're talking about your Ubuntu's or all of these things. So how do you manage packages? That's what I'm talking about. And that all runs on top of the kernel. So we have our user. All right. So this is, and when you're talking about an OS in a hypervisor like this, in a VM, your OS has the user space and the kernel and everything. And so then, then you have whatever, Postgres, whichever your favorite database is, Postgres, whatever. And this is the VM model. Now, let's put that against the container model. We still have our base machine here. Now, this base machine could be a VM if you wanted it to be. And it still has its hardware. If it's a VM, it would have its virtual hardware. But again, it's hardware. And then this would then have its OS. And let's break this down evenly like this. It would have its kernel. And it would have its OS on top of that. So whether you're Ubuntu, Red Hat, Fedora, CentOS, Arch, Gentoo, whatever. I'm trying not to offend anybody by leaving out there. I know that I left out a ton, but all right. SUSE. And yes, SUSE, SUSE. That's how it's pronounced because it's a German company. So that also means it's Porsche for, I don't know, I'm not really a car person, but I found that out. I know some Germans. Anyways, I called it SUSE for the longest of time. Anyways, so we have our OS here, and then we have a container engine. You don't really have to have the container engine, and when we do containers the hardest way, we're going to make our own container engine. We're going to do everything. Everything that the container engine does exists in the kernel here. So technically, you wouldn't have to have a container engine, but a container engine like Docker, Podman, Cryo, whatever, makes things much easier. So I'm going to put an asterisk here, as this is technically optional, but it's not really optional because you would never want to go into production. It's not really optional, okay? Kubernetes needs the container engine to schedule. So if you didn't have a container engine, you couldn't use Kubernetes. And if you couldn't use Kubernetes or other pod schedulers like Nomad, you would be impossible to use those tools. And if you couldn't use those tools, why are you using containers again? Anyways, there are some other uses for containers. Don't get me wrong. I'm not saying they would be completely useless. Build scenarios, they would be fantastic. All I'm saying is that you completely get rid of most of their usefulness. All right, so we have container runtime. I say container runtime, container engine. All right. Now, this is where things really start to get different. You say hypervisor, container runtime. So far, it's really been the same thing. All right, let's now look at this. You'll notice here these two things, and really this one has the kernel in it. So you'll say, but Merrick, I can build a Ubuntu-based image. And I will tell you that that is a Ubuntu user space. So that means you have apt in the image. You have Ubuntu repositories that you can install with apt in your Docker file or however you build it. That is what it means. It does not mean that you have the Ubuntu kernel. You don't. In this setup, you use exactly one kernel, your host OS's kernel. So Why this is important to know, there's a couple reasons why it's important. One, your kernel on your host machine makes a difference, and it matters because the kernel that's sitting here outside the containers at the root of containers is the kernel that all your containers are going to get. So if there's a security vulnerability in your kernel outside of your containers, there's a security vulnerability in your kernel inside your containers. Okay? I just want to make sure that that is clear. I don't think a lot of people understand that. You don't have all of Ubuntu running. So let's say this OS down here is SUSE Enterprise Linux. SUSE Linux Enterprise Edition. I don't know. It is SLES. I don't know what it stands for. SUSE Linux Enterprise Systems. Anyways, I'll figure that out and I'll post it up here. All right, so here we go. SLES is right here. And then we have this Ubuntu image here. And let's just give this SLES a kernel version of 4.1. That means here, the kernel this is using is this one. And it's 4.1. Over here, where our OS was whatever it wanted to be, our OS could have a kernel over here of 5.1, and the OS up here could have a kernel of 2.1, or whatever kernel. You would not want a kernel. That's a really old kernel. Okay, so that is really the biggest difference, because now that we're sharing the kernel of Linux, really, that's it. You run whatever you want here in the container. You could literally pass it just nothing else except your script, as long as your script had no dependencies on anything else to install, it would work. And these base images of Ubuntu or Cubic or whatnot that you install, or Alpine, basically just set up the bare necessities of the user space for that flavor of Linux. But you're still running everything down this stack. All right, so this is very quickly containers versus VMs. The real difference is whether you share a kernel or not. In this model right here, what we really want to know is how we safely and securely share a kernel. So then there's really two tools that allow us to do this in a safe way. Now, there's actually a lot more that goes into containers. So when I say two tools, I mean two major technologies that do this. I don't mean that it's limited to just these two tools that are used or anything. And you'd have to look at the container runtime implementation. There are several different container runtimes. Easily, I can name 4. Kata container, Cryo. Kata's actually a special case. We can get into Kata, but let's scratch Kata containers off the list. Let's scratch them off the list. I think that it's not that they're bad. I just don't really consider them containers. It would be like calling Firecracker containers. But anyways, Cryo, Podman, Docker, you'd have to look at their implementations and how they handle these things, because really, Linux containers. That's the other one that I was thinking of. Linux containers is actually, it's a little confusing. Linux containers, LXD, is a container solution. So if you're looking that up, but I mean, Docker is running containers in Linux. I mean, so that's a little confusing because all containers are Linux containers because they're using the kernel resources. Even when you run Docker on Windows, I haven't run Docker on Windows for like 2 years, so don't quote me exactly. But when you're running Docker on Windows, you are running a Moby Linux engine in Hyper-V that's running the containers, and they're just doing some magic to port it out to Windows. So all containers are Linux containers, but there is a technology called Linux containers that runs containers. My only point here is that to find out exactly how all of these do the things, you would need to look into each individual one. And that's something we can do. It'd be a great learning experience. But But these are some of those tools that they use in general. Not that they are limited to these tools or have to use these tools. So let's dive in. The very first one that I want to point out is namespaces. And namespaces are pretty simple, and they're something most developers, most programmers are familiar with one way or another. So when you're thinking about code, you've literally seen the word namespace if you've written C, C++, C Sharp. You have these things called namespaces. In Java and Java-based languages like Go, I know I made every Go programmer angry at the exact same time, but look at it. It's basically stripped down Go. You have these things called packages, which are equivalent to, well, not equivalent, not a great word to use there, but they are similar to namespaces. So you look at these things and you'll see that it's a way to segregate out what sees what. And that's all Linux namespaces are in the end as well. They just allow you to segregate. So classically, you can segregate out the PID. So it looks like it's running its own PID. And we can do that. And we will do that in the containers the hardest way, where we actually run a process, we'll run bash as its own process. And it will have a PID of 1 because it's the first one in its tree of execution. So if you know how Linux runs processes, there's this tree of execution. And if you're familiar with trees, it looks something like this. And so PID of 1 is classically reserved in Linux as the system in it. Talking about systemd, there are a few distributions that don't use systemd. I think Arch you can run without systemd. I think they do support some other ones. And then Debian, a Debian-based one that also doesn't run with systemd. But as a systemd, it would be systemd would be the thing that runs as PID1. And so that's here. And then it has its child processes. And, this child process is over here and points directly here. This one points here and blah, 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 blah. What you can do with Linux namespaces is cordon this off so it can't see its parent. It cannot see this. Let's give it a PID of 5. It can't see it. And it's going to not know anything else. It's going to think it's the only process. Right now, as of right now with namespaces, it can be used with control groups, which is next week's video. IPC, network, user space, PID, mount, and I know that there's at least one more. 1 second. I'm gonna have to look it up. UTS, so the host name, and NIS domain. So those are some of the ones that you can control. And what it allows you to do is partition these things off so that they cannot see outside their namespace. And so you can also then put multiple processes in one namespace. So in this example here, you can put these 2 processes in that namespace, and they also cannot see out. So this is what namespaces does. Now, one of the caveats which you don't see here is that these processes in this namespace here can access all resources, meaning they can use as much memory as they want, and they can use as much of the processor as they want. Namespaces don't give a way to control the amount of resources. They only give a way to partition them off from seeing other ones. And that's where control groups come into play, or as a lot of people call them, C groups. C groups are what is going to enable us to do that. And we're going to cover those next week with hopefully a mini Mighty Monday and not a major Mighty Monday. I hope that you found it educational. I hope that you learned something from it. All right. I hope that you like this. If you do, please like and subscribe. You know the drill. If you didn't like this and you're still here, go ahead and hit that subscribe button. Leave a comment down below on why you didn't like it, but still stuck around. Stick around and see if these videos get any better for science.